He didn't have that. He had Lou Garrett. Not. It's ALS. He had ALS. It's Stephen Hawking. I do not know. Sir, yeah, I think that sounds right. So, I passed out some notes. Forgive the quality, Miss England. I got all my notes from her. And she had everything on physical, so I had to scan it and digitize it. So, a lot of these worksheets are going to be kind of faded. But here are some useful constants and some formulas. Density is mass over volume. Avogadro's number. Avogadro's is 6.022 times 1023 particles per mole. And a particle could either be an atom or a molecule. Speed of light. Most of these we won't use. Again, I make notes that I use the full definition, 273.15. Volume of an ideal gas at STP is 22.4 liters per mole. Conversion factors, it's 325. Should be at the end of that. There should be a 4 at the end of this. 1 calorie is equal to 4.184. Again, this is stuff Miss England had. I use more technical stuff, or more, I should say, more precise. So behaviors of gases, these are going to be our laws. So we can take the combined gas law, break it apart. Note that the combined gas law has an extra term in here. It uses the ideal gas law. But this is unimportant right now. It's just a list of constants, a little refresher. We'll mostly concern ourselves with is the gas laws. So we have Boyle's law, Charles's law. Note it's a misspelling. It should say Gay-Lussac, not Guy. And then a combined gas law, and writes it in various forms. Again, I prefer the equations where all the initial variables are on one side, all the final variables are on the other side. So let me pull up the PowerPoint from yesterday that we didn't finish, and work through some examples. So again, this class does use algebra. You are expected to know algebra in this class. And we also have the additional difficulty of units. So this problem says a gas occupies 473 cubic centimeters. Let me write this down. A gas occupies 473 cubic centimeters at 36 degrees Celsius. Find its volume at 94 degrees Celsius. So, first general step to solving physics or chemistry problems. Identify variables in the equation. So a gas occupies 473 cubic centimeters. What variable is this associated with? Is that mass? Is it grams? The volume. This is the initial, so this would be V1. A temperature of 36 degrees Celsius, so that would be T1. And ask you to find its volume at 94 degrees Celsius, so that would be the final temperature. And we're trying to find V2. So, if you just memorize this equation, P1 times V1, or really all you really need to memorize is this. PV over T. If you remember it's PV divided by T, then you can rewrite this with 1's beside it and set equal to it again, and now put 2's beside it. If it doesn't talk about one variable in the whole problem, we assume it's constant and unneeded. So, for example, if I have 5x is equal to 5y, 5 times something on this side is equal to 5 times something on the right side. Is the 5 important? What would happen if we divide both sides by 5? It'd be 1 times x is equal to 1 times y, or just x times y. So in this problem, it doesn't talk about pressure, so we can assume pressure is constant and doesn't change. I.e., initial pressure is equal to final pressure. So this pressure is the same as this pressure, so it's like having the same number on both sides. We can remove it from the equation. And this combined gas law will be converted and become Charles's law. So the combined gas law becomes Charles's law. So this is an example of Charles's law. We're only changing temperature and volume. So we have the equation V1 over T1 is equal to V2 over T2. We know that V1 is equal to 473 cubic centimeters. What would T1 be? Nope. So is this a change in temperature? It is not. It is an absolute temperature. It's a specific value. So that means we need to take the 36 degrees Celsius, add 273.15 to it, and we get a value of 309.15 Kelvin. So T1 is 309.15 Kelvin. T2, same thing, 94 degrees Celsius. We need to use Kelvin, so we have to convert it. And that would be equal to 367.15 Kelvin. This is our equation. These are our variables. These are what we plug in. Personally, I use pure algebra until the last step. What are we solving for? We're solving for V2. So if we're dividing by final temperature on the right side, to cancel it out, we'd multiply T2 to both sides. T2 divided by T2 cancels each other out, and we're left with T2 times V1 over T1 is equal to final volume. So final volume would be equal to T2, which is 367.15 Kelvin, times V1, 473 cubic centimeters, divided by T1, 309.15 Kelvin. Notice that Kelvin cancels each other out, giving us only cubic centimeters as the remaining unit. So 561.74 cubic centimeters. So if you were to take a gas, so for example, if you had a balloon filled with 473 cubic centimeters at 36 degrees Celsius, if you increase the temperature of the gas in the balloon to 94 degrees Celsius, its volume would go from 473 cubic centimeters to 561.74 cubic centimeters. So this doesn't deal with pressure. So again, we extract our given. Volume 1, temperature 1, make sure you convert temperature into Kelvin. We're looking for its final volume, and its final temperature is 367.15. Again, I'm more precise than a lot of these examples. There's no reason really to round whenever it's just 0.15 to be exact. So this is an example of Charles' law. I highly recommend doing this. Charles' law says that temperature is directly related to volume. What that means is as temperature goes up, we would expect volume to go up. Now note in this PowerPoint, they do it differently than me. They begin with this version of the equation. Because pressure is equal to so initial pressure is equal to final pressure because it stays constant. It's not mentioned in this problem. They eliminate it from both sides. And so filling in the variables, to solve for V2, you would divide by 309 on both sides, and you get V2 is equal to 562, which is rounded to 3 significant digits here. And note that my answer was more precise than theirs. Technically, this answer will be rounded to 2 significant figures if we're doing significant figures, but from this point on, I don't think I'm going to be grading in significant figures. You'll note on the test, significant figures are still used, but it's not going to be asking you to select the answer with the significant figures. For example, like the answer might be, I might round to 2 significant figures. So you'll see answer choices like 0.15, 25, and 2.7. All the numbers will be different. You notice on the last 2 tests, I had to ask the question, what is the correct answer? And you saw that there are 5.1, 5.11, 5.101, and all that. They're all the same number, just rounded in different significant figures. And moving forward, the test isn't going to do that. They're all going to be different numbers. They're just going to be rounded to so many significant figures. So there's no going to be trick question where you have to identify significant figures. It's just going to test I use significant figures in the answers. What that means is if you saw on the test, you might see 560 cubic centimeters, even though the calculator gave you 561.74. You should just know that that's the choose an answer closest to what you get your calculator against, basically, right? So if you saw the answer is 320, 450, 560, or 980, you know that the answer was about 560, so you choose that. So on the test, I will be rounding mostly to significant figures. On any of the tests, there's multiple choice, but just know select the one that's closest. So let's do another example. A gas occupies 100 milliliters. Again, that point after the 100 is improper, but it does mean that there are 3 significant figures. I told y'all should not write numbers like that, but generally they do this on questions because writing it in scientific notation is kind of difficult to do on a PowerPoint, so they usually don't use scientific notation. They put that period to indicate that all 3 of these numbers have 3 significant figures. So a gas occupies 100 milliliters at 150 kilopascal. Find its volume at 200 kilopascal. So again, same thing. Come over here and identify your variable. If a variable is missing, like for example, if temperature isn't talked at all, we'll assume it's constant. So here, this is volume. It's your initial volume. Kilopascal, you have to memorize that kilopascal pressure. So that's your initial pressure. We are looking for its final volume at a final pressure of 200 kilopascals. So V1 is equal to 100 milliliters. P1 is equal to 150 kilopascals. V2 is what we're looking for. And P2 is our final pressure. Since there's no temperature, we'll assume it's constant. So P1, V1 over T1 is equal to PV over T. And just put 2's on everything. 1's on everything on the left. Since temperature is constant, we can remove that from the equation. And this becomes Boyle's law. So P1 times V1 is equal to P2 times V2. We are solving for V2. So to get V2 by itself, we divide by P2 on both sides of the equation. P2 divided by P2 cancel each other out. And so we're left with V2 is equal to P1 V1 over P2. Once you do the algebra, you just plug it in. So P1 was 150 kilopascals. V1 is 100 milliliters. and P2 was 200 kilopascals. Note the units kilopascals appears on the numerator and the denominator, so they cancel each other out, leaving you with milliliters. I recommend always using units because it might be a trick question and where one number is in liters and the other number is in milliliters. If they don't cancel each other out, you'll need to do some conversion factor to it. So you might need to convert by doing 1,000 milliliters to 1 liter or something like that nature to this equation to cancel out milliliters and get you liters. And this is equal to 75. Our unit remaining is milliliters. So that's our answer. So what this says is if you increase the pressure of a gas from 150 kilopascals to 200 kilopascals, its volume would change from 100 milliliters to 75 milliliters. And here, since we're using Boyle's law states that pressure is inversely related to volume. So again, to make sure you didn't do a math mistake, let's check. So we know that as pressure increases, volume must decrease. So we started with a volume of 100 milliliters. According to Boyle's law, volume is going to get smaller. So again, they wrote their given variables. I realized that this doesn't deal with temperature, so it has to be Boyle's law. As pressure increases, volume must decrease. And they started with the combined gas law. Again, this PowerPoint uses this version of it. Doesn't matter, temperature is going to be removed. And so they worked it out. They plug in numbers before doing algebra. I do algebra first. I tend to never plug in numbers until the very end. And they got 75 milliliters. Note they put 75.0 because of significant figures. So let's do this last problem. A gas occupies 7.84 cubic centimeters at 71.8 kilopascals and 25 degrees Celsius. Find its volume at STP. So here is its initial volume. Here is its initial pressure. And here is its initial temperature. So V1 is equal to 7.84 cubic centimeters. P1 is equal to 71.8 kilopascals. And T1 is equal to 25 degrees Celsius, but we need to convert that. So we add 273.15, so that's equal to 298.15 Kelvin. we know that standard temperature and pressure. So we're looking for final volume. The standard pressure, P2, is equal to 1 atmosphere, which is also equal to 101.325 kilopascals. Oh, and sorry, forgot that y'all couldn't see. So initial volume, initial pressure, initial temperature. We need to convert temperature here, and we know that final pressure, the standard pressure is 101.325, and the standard temperature is 273.15 Kelvin, or 0 degrees Celsius. So here we have all three variables in. So when we do our combined gas law, we can't remove anything. So we will have to use combined gas law in its full. So we are solving for V2. Here's an algebra trick for you. So I'm going to rewrite the equation. P1 V1 divided by T1. By the way, here is V2. V2 is being multiplied by P2 and divided by T2. So it's being multiplied by this fraction. P2 divided by T2 is being multiplied to V2, right? V2 is being multiplied by V2 and it's being divided by T2. If you have a fraction multiplied against your variable that you're solving for, you can multiply both sides by the reciprocal. The reciprocal would be T2 divided by P2. T2 divided by T2 cancels each other out. P2 divided by P2 cancels each other out, and we're left with just V2. So V2 is equal to P2 P1 V1 divided by T2 T1. So now just fill in the variables. That's 101.325 kPa. I made a mistake. Anyone recognize the mistake? When I multiplied the reciprocal, that's not the reciprocal is T2. Divided by P2. My bad. So you multiply the reciprocal to both sides, T2 over P2. Let me just redo that. So we started with P1 V1 divided by T1, and that is equal to P2 V2 divided by T2. We multiply both sides by the reciprocal, T2 divided by P2. This time don't flip them. So we're multiplying to both sides. T2 and T2 cancel each other out. P2 and P2 cancel each other out, giving us just V2. So V2 should be equal to T2 P1 V1 over P2 T1. Here's a good question. How did I instantly know I made a mistake? Because I looked at the units on all the equation. I knew I made a mistake as soon as I got to the units. The units for this would have been kilopascal times a kilopascal times our volume is cubic centimeters, and it would be divided against a Kelvin times a Kelvin. Is this the units of a volume? This would have been kilopascal squared times cubic centimeters divided by Kelvin squared. None of the units cancel each other out. This is another reason why I highly recommend you actually write the units and cancel them out, because it is very, very easy when doing algebra to make a stupid mistake like I just did. Now, whenever I come in here with my equation, regardless of if you did the algebra right, if you plug in all these values, as long as you plug them in correctly and you write units, if they cancel out, you're guaranteed to get the correct answer. So temperature 2 was 273.15 Kelvin. Pressure 1, making sure I'm coming up here and writing the correct pressure. So pressure 1 was 701.8 kilopascal. Volume 1 was 7.84 cubic centimeters divided by a pressure 2 of 101.325 kilopascal, and divided again with another temperature 1, which is 298.15 Kelvin. Before I even reach for a calculator, I check to see if units match up. Did I make any mistakes? A Kelvin on the numerator and a Kelvin on the denominator, this cancels out. A kilopascal and a kilopascal cancel each other out. I am left with the units of cubic centimeters, and cubic centimeters is a unit of volume. I know this has to be correct because the units line up. This is dimensional analysis. I don't know if I ever explicitly told you this. In dimensional analysis, the dimensions are units. Another name for dimensional analysis is unit analysis. You're analyzing units. In science, we call units dimensions. You have so many. You have so much value in a certain dimension or a certain unit. So when doing this, I get 5.08967 and my remaining unit is cubic centimeters. Everyone good? So again, they use the alternative formula. So again, get all your values, convert temperature. This is the combined gas law because it measures all three. We know that as pressure goes up, temperature will go down, and also volume will go down. So as pressure increases, temperature and volume must decrease. So they use this version of it. Nothing cancels out, so you can plug in your variables. And you can see here that to get V2 by itself, you're going to have to divide by 101 kilopascals and 298 Kelvin to both sides of the equation. Doing that, you get 5.09. Note, when typing into a calculator, if you're doing 101 times 298, you need to put the entire denominator in parentheses. order for it to look. Again, my calculator is more fancy than y'all's. But if we look, I did 273 times 71.8 times 7.84. And then I did division. And then in the denominator, I put the entire denominator in parentheses. So make sure that your entire denominator is in parentheses. Alternatively, this is why I like using the grid. I could have just multiplied everything on the numerator together, and then divided by all the denominator one by one. So hit divide by the 298. It looks different, but it gives you the same value. Personally, I recommend just doing denominator always in parentheses. Here's a good point to give the code word. So here's the code word. So let's review each of the laws. Boyle's law deals with P times V. It basically states that as pressure goes up, volume goes down, or as pressure goes down, volume goes up. This is an inverse relationship. Can you think of some examples of Boyle's law being used? And again, this assumes constant temperature. Hold on. Is this correct? As pressure goes up. Yeah. Another way of saying this is as volume goes down, pressure must go up. Or as volume goes up, pressure must go down. So can y'all think of an example in which one of these occurs? What happens if you take a can of Coke and you squeeze on it? Or take a water bottle, an empty water bottle. What happens if you squeeze on it? What happens if you're shrinking it down? So as I take this empty water bottle, I squeeze the volume down. What's happening to the pressure inside? It's getting stronger. So as I decrease the volume of this bottle, the pressure is going to increase. Pressure is equal to force divided by area. So the area of this lid stays constant. That means that as I'm squeezing, as pressure is going up, the force of the air molecules hitting this bottle cap increases. So if I squeeze really, really hard, I would eventually expect the force or pressure to increase to where the lid comes off. So as I decrease volume, pressure builds up inside. So that's an example of Boyle's law. So let's look at, can anyone think of another example? That's higher. So as the pressure decreases, The tire gets bigger. So yeah, if you well, as you increase the pressure inside of it, it usually gets bigger. So if you have a flat tire, and I were again, this still doesn't work because the pressure is going to stay at atmospheric pressure until you get to a certain point. I don't think that quite fits Boyle's law because how do you increase? Okay, that's actually a good point. All three of these laws depend on constant mass. When your tire is leaking, are you losing air? You are losing mass. So the reason your example doesn't apply is we're not having constant mass. So all three of these laws deal with constant mass. This one, Boyle's law, also has constant temperature with it. So if you're losing mass or gaining mass, this doesn't work. Because when you're blowing up a tire, you're increasing its pressure, but because you're adding more mass to it, the volume also goes up. So you notice it doesn't work in this case because mass is not constant. That is a very good point, actually. So another example would be, have you ever seen a movie where someone takes off their helmet? And and their face starts to swell. So what happens is they basically take the volume of gas inside the helmet, and then they open it to space, so the volume of the gas increases, which means the pressure decreases, because the volume increases, the pressure decreases. And because I said the reason why you don't feel any pressure is because you have internal pressure. So the pressure pushing the skin down and keep it maintaining your shape disappears because it decreases a lot. And so a person will start swelling up as the only pressure is the internal pressure and you see them swell up. By the way, what would happen if you... how much time do I have? Okay. How much? I have... Yeah, let me... No more of that example. I need to go over this. We'll have a lab tomorrow. Bring Coke cans. The more you bring, the more we'll do. I should bring some, but I'll only bring enough for the class. So, Charles's law deals with volume over temperature, and it's a direct relationship. What this means, as volume increases, temperature increases, or as volume decreases, temperature decreases. Or as temperature increases, volume rearrange it. And this assumes constant pressure. All of them assume constant mass. So examples of this is anyone take a can of air and spray it? Or any can, a can of deodorant. What does it feel like whenever it hits you? Does it feel super cold? So you have inside of a can some gas at a certain volume. As it comes out of the can, increases to a bigger volume, so volume goes up. Now, again, that's decreasing mass. I'm trying to rush because I only have a minute. That example. That's an example of pressure. So what happens if you compress a gas really fast? So think of an engine. This is more example. An engine. So we have a piston, right? We have a piston. As this piston pushes down, it compresses. Again, this is I'm running out of time. This is also a different example. This is dealing with something else. What's a good example here? This is a hot air balloon. So if we have a low gas and we heating it up, it's at a certain temperature, and then as the temperature rises up, the volume is going to increase. This is it. So volume. I'll quickly go over this tomorrow. But we'll have a lab tomorrow and investigate this. For remote learners, because I'm using the same video, I'll continue. We also have Gay-Lussac's law. So I'm not going to have a video tomorrow. Gay-Lussac's law states that pressure and temperature are related. This assumes constant volume. This is more of the deodorant example. Or this would be more of, we have a can of Coke. As we have the gas staying at constant volume, if we were to increase the temperature, what would happen is the pressure would increase. So as pressure increases, temperature increases, or as pressure decreases, temperature decreases. So if we were to increase the pressure of this can, the temperature of the gas is going to get hotter. Or another way of saying it, as we increase the temperature, pressure goes up. That's it for the day.